So let's consider some of the reactions of acyl chlorides and acid anhydrides. They are similar and they do show certain patterns, so watch out for these patterns. So ethanol chloride and water, let's begin with. They will react together and react together quite violently, and they will produce ethanoic acid and steamy white fumes of HCl. Now, ethanol chloride reacting with an alcohol, such as ethanol, follows a similar sort of pattern, but instead of getting a carboxylic acid, we get an ester, ethyl ethanoate in this particular case, and, surprise, surprise, steamy white fumes of HCl once again. Now once again we get a very similar sort of reaction between ethanol chloride and ammonia, but there are some slight differences in this. Just as we produced a carboxylic acid with water, an ester with an alcohol, and with ammonia we're going to produce an amide. But instead of getting misty white fumes of HCl, we'll get the ammonia reacting with the HCl to form ammonium chloride. So in this particular case you will find you'll be requiring 2 moles of ammonia. Reaction of ethanol chloride with amines, methylamine, follows a similar pattern to the reaction with ammonia. We're going to get an amide again, but this time it will be a nitrogen substituted amide, and instead of getting ammonium chloride we're going to get the ammonium salt of the amine, so methyl ammonium chloride in this case. Two moles of methylamine, you'll notice, reacting for this. Acid anhydrides follow exactly the same sort of pattern, but instead of forming HCl, you will get the carboxylic acid. So with water, you will get ethanoic acid plus, surprise, surprise, ethanoic acid. With the anhydride and an alcohol, to ring the changes I've taken phenol, which is an aromatic alcohol. In this case we will get, if you think about it, an ester. This will be phenyl ethanoate as our ester, and carboxylic acid, ethanol. Reaction with ammonia, again we're going to produce an amide, and the salt of the carboxylic acid, the ammonium salt of the carboxylic acid. 2 moles of ammonia once again reacting to give the amide and the salt of the carboxylic acid. And finally, ethanoic anhydride plus an amine is going to give you a nitrogen substituted amide plus the salt of the carboxylic acid, the alkyl salt, alkyl ammonium salt of the carboxylic acid. And I will leave you to fill in the empty spaces. So the mechanism for reaction of acyl chlorides and acid anhydrides with water, alcohols, ammonia, or even amines is an addition-elimination. So let's take something like, let's say, ethanol chloride, and have a look at the mechanism as it reacts with methanol. Now, why would these two reactants react together? Well, oxygen is a highly electronegative element, the second most electronegative element in the periodic table. Therefore, it's going to be pulling electron density away from the carbon, as is chlorine, of course, delta negative charge on there. So we've got a big delta plus charge on that carbon, and that carbon therefore is going to be susceptible to nucleophilic attack. And of course the oxygen of the OH group is a nucleophile. It's got an available lone pair of electrons which it can donate. So we're going to get nucleophilic attack of that carbon by the OH, or the oxygen on the OH group. So you can show a curly arrow from that towards the carbon with the delta plus charge. Now that carbon of course has 4 bonds. It has no space for an extra electron pair, so it's got to release a pair of electrons, and the pair of electrons that it will release will be the weakest bond, which is the carbon oxygen pi bond. So we'll find that that pi bond will break, pair of electrons moving towards the oxygen like that. So that's the first step, and our intermediate, of course, to show all the bonds broken and all the bonds that have formed. We've broken the carbon oxygen pi bond. We're left with carbon oxygen sigma bond there. Carbon chlorine bond is still there, and we have a new oxygen hydrogen bond, oxygen carbon bond there, CH3. Of course, oxygen here has essentially used a pair of electrons to form that oxygen carbon bond. The oxygen, you will notice, has 3 bonds. It will therefore have a positive charge. It's essentially given one of its electrons to carbon, which has been used to form that carbon oxygen bond. Oxygen, of course, has not only taken its own electron from that pi bond, but also carbon's electron, so we've got a negative charge there like that. So that is intermediate. So you can imagine that what's happened is that that pair of electrons have flown up to the oxygen, now they're bouncing back, and we are reforming a carbon oxygen pi bond, and we will release the carbon chlorine bond like that to produce this. Final step is loss of the proton. Now that loss of proton could occur in that step as well. No reason why you can't put it there, but we will get finally CH3, C double bond O, OCH3 plus H plus Cl minus, and of course that will produce HCl.